Okay, it is time, but I'll wait for another minute to see if some other participants also join. Okay, so I'll start the lecture now. So welcome everyone for this afternoon lecture on simulating astrophysical fluids. So what I'm going to talk about is some of the basics of how we perform computer simulations of fluids and apply those techniques to study the evolution of astrophysical fluids for different purposes. Now, this is something that I personally work on, and this is something that I'm also very much interested in. But it is very difficult to cover this technical subject in a short 1 hour lecture. The best way to demonstrate this is actually a hands-on session spread over a few days, but we don't have the time for that in this. So what I will try to do is give you the basic flavor of what exactly are the things that we have to account for when we actually talk about simulations, computer simulations, uh, and introduce one particular simulation code called Pluto. It is an open source, widely used astrophysical code for astrophysical simulations, and I am also closely involved with the developers, and show you how you can set it up so that it is quite easy to understand as well. Well, easy to use. To understand it takes a lot more experience and more hands-on um, hours to master the code. But if you have a problem in mind, simple textbook problems that you have learned maybe in your courses for fluid dynamics, you can readily use this code and start simulating those to understand their behavior better. So let us begin. Oops. Yeah. So the basic theory of the numerics that I will discuss today in the first part of the lecture is more broadly based on this very well-known and widely used book called Riemann Solvers and Numerical Methods for Fluid Dynamics by Toro. And the chapters relevant for the discussion today will be this list of chapters. This will be uploaded on the course PBWorks website. So 2, 3, 4, 6, 9, and 10. Of course, I'm just giving you the references so that in case you ever work on some project or something related to numerical simulations, you can come back to these and then read these chapters in much more detail to understand the numerics better. And the code Pluto that I was talking about can be freely downloaded from this website. You will all get these PDFs on the PBWorks page. Okay. So before we begin on the specifics of the numerics of the simulation, I wanted to give you a broad overview of the kinds of simulations people actually do. So broadly speaking, we perform simulations. So in order to understand the evolution of astrophysical objects and fluids and gas in space all around us, we can simulate them in our computers by following the evolution, following the equations of fluid dynamics. Now, in terms of the types of simulations, people usually simulate them in two broad classes. One are the particle simulations, where this is the basic formulation of the physics itself. So particle simulation are two types essentially. So you actually start and try to simulate the interaction of different particles. Of course, in an actual gas, we all know that gas is described as a fluid, but is actually composed of particles which we have a broad volume averaged view from thermodynamics to describe the large scale properties. But they're actually made of particles of ions and electrons if they're ionized in plasma or neutral particles. Of course, in simulation, you really cannot simulate billions of particles. Then that would be quite taxing. So what we do is we assume that a single artificial particle is a collection of particles, or called something that is called a macro particle. And we evolve the motion of these macro particles guided by the basic formulation of the physics, what we want to study. For example, if it is just the gas dynamics from a particle point of view, we evolve the motion of this collection of ions and electrons, or macro particles of ions and macro particles of electron, which are interacting with a background electromagnetic field. And this kind of simulations, for example, are called the particle in cell simulations, or PIC simulation, PIC. On the other hand, a particle description is also very much valid for studying systems, for example, say a globular cluster, or even the stars inside a galaxy. Each of these stars, or the clusters of stars, can be represented by a particle that represents a star cluster. Again, the same concept. You have a macro particle that represents several stars, but there are millions of stars in this particular galaxy, and then we can understand the dynamics and the kinematics of these particles moving due to the mutual forces of gravity and other interactions. So as I've written here, we either this kind of uses would be modeling stellar kinematics, galaxies on large scale, or even on smaller scale plasma simulations, where you're not describing the thing as a fluid, but more as an individual motions of particle. So this would be covered by the first type in this domain, called the motions of macro particles. But then there is another called smooth particle hydrodynamics. And in your fluid dynamics lecture, I am sure you've now heard this term about Lagrangian motion and Eulerian motion. In Eulerian motion, we divide the background fluid in a grid. And then we just evolve, we see how the properties of the fluid are changing as at different locations in space. But in the Lagrangian motion, we discretize the fluid in terms, or represent the fluid all around us in terms of particles, which have a single point in space represents a blob of fluid, for example. And then we follow the motions of that fluid blob. And that is called a smooth particle hydrodynamics. This is a very crude way of saying it, by the way. And I have to devote a whole other lecture to this. I just wanted to let you know there is something also called smooth particle hydrodynamics, where we actually follow the motions of particles. And then we assume that the properties of the fluid at the location of the particle are given by a kernel function that connects the particle with the background space. So in this type of simulation, there are pros and cons. So the challenges that we face are, since there are many body interaction, we have to calculate the individual interaction of all the particles with each other. Also, since the particle trajectories can be arbitrary, you need to have an adaptive system where you can resolve the length scales. Otherwise, the particle motions cannot be tracked with the uniform accuracy. But the good thing about this is is a resolution. In a normal fluid simulation, say suppose you have a box and you discretize the space into individual elements. There are some regions where there are higher density of particles, while there are high density of mass or gas, let's say, and other regions where they are lower density. And you do not need to resolve the low density parts that well, because you're not really interested in them. But in a standard Eulerian system, or a fluid or a discretized fluid description, you have to uniformly resolve everything, or in some way also discretize. But with the particles, you can choose to resolve the regions where they have the highest densities as compared to others. So this is one advantage of particles. Of course, in the fluid description, more tricks have been evolved. For example, the adaptive mesh refinement. We have nested meshes or nested grids which are denser in certain locations and rarer in certain locations, but that leads to loss of errors when you're actually computing the equations. So that is a particle simulations. And now the other part are fluid simulations. So fluid, as I said, a fluid description, as you must have heard in your lectures by Nishant and Drupaditya, is valid when the mean free path of the particles are much smaller than the physical dimensions. Then the basic properties of the gas, for example, density, the pressure, temperature, etc., are evaluated as volume average quantities over a certain spatial region. And this is what, and thus we can describe the entire gas as a continuous distribution of the different functions. And that is when the fluid description is valid. So do keep in mind about this particular criteria. There may be certain occasions where it might look like a fluid, but if you calculate the mean free path, you will find that the mean free path becomes comparable to the physical dimensions over which you want to study some phenomena. And there, a particle description then becomes more apparent. For example, this is often the case for intracluster medium or ICM, where the fluid is extremely rarefied, and the particle interactions becomes collisionless, and it is better to be represented as a particle than a fluid. So what are the major challenges of fluid simulation? The major challenges is to have sufficient resolution to reduce numerical dissipation. And then we have to also discretize the space, and thus this gives us a definite geometry that we have to assume. For example, it can be either a Cartesian or spherical, etc. So if we assume a Cartesian geometry, then any other kind of, if the flow itself has a symmetry of its own, since we are discretizing the space and that is an approximation, some of the flow properties are not well caught due to the discretization. For example, if you have a Cartesian coordinate system, and if you are modeling a spherical flow in a Cartesian geometry, then you invariably lead to this some instability called the carbuncle instability, where the edges of the grid start showing funny behaviors due to the poor discretization of the space. The way to resolve this is just increasing the resolution, so your small cubes are well approximate the. So if your radius of the sphere that you're trying to simulate is much larger than the smallest size of the cells of the cubes of the discretized space, then you're fine. So these are some of the challenges we face. And both this kind of simulations are used. I will not talk about the first part. I will mostly focus on the fluid simulations for the rest of the lecture. Just giving you an overview of what kind of computing languages we require. So we are all familiar nowadays with some basic computing languages, which are quick to use and useful for producing quick analysis and plots, etc. Some are like, for example, Python, IDL, MATLAB, etc. But these are quite slow. For large-scale fluid simulations, these are not helpful. For this, we have to go to some basic languages like C, Fortran, C++. But again, what the problem is, since we are trying to model actual astrophysical phenomena over very large spatial scales, we cannot often run them on a single processor or a single computer, a single desktop. So then we have to use parallel computing architecture, which Ajay has been teaching you for the last few lectures. And the typical languages are MPI-CC, MPI-F90, or the message passing interface, MPI, for different sorts of basic compilers. So for this, what we do is we divide our entire problem into smaller subsets, and we allocate each processor to carry out a certain task and essentially distribute the problem into several different computers and then run them simultaneously. So what is really important for this kind of system, this kind of a parallelized environment is very fast interconnectivity or a very fast connection between the different computing nodes. And that is why it is not simply the fact that you buy several desktops and connect them with wires and then you have a good cluster. you have to have very well specifications that you have to meet. Otherwise, you'll slow down your code. And I'm sure Ajay has talked about the fast message passing interface, the InfiniBand connections that transfers information from one code to another, etc. So I'll not go into all of this. Now, so this was the standard way of simulating things till about 10 years back. But nowadays, in the large-scale supercomputing facilities, a hybrid nature mode of computers are being developed, where you have a GPU card that is talking to the CPUs. And it is a GP-CPU interface that is often used because the GPU has several threads, and you can run things very fast if it is easily parallelizable. And then below the GPUs, you have the standard network of computers. So some of the major clusters are actually moving towards this sort of architecture, mainly because for having a larger cluster with several different cores is extremely power consuming. Whereas if you can modify your code to make it efficient such that it can run both on GPU cards as well as CPUs, then the power budget goes down significantly. And nowadays, as we are going to the exascale, right now, most of the clusters are in the petascale computing. So at each second, you have peta flops, 10 power 12 flops, floating point operations. Now we're going to exascale, so 10 power 15 floating point operations per second. And this kind of hybrid systems are being conceptualized for that. And just to give you a rough example, the large-scale simulations, for example, that I perform, they're often required to be run on 2,000 to 3,000 processors per simulation. I run them for 24 hours, I check the data, and I keep on running them. And each of my model, let's say, takes about a week to run. So the actual cutting-edge research is extremely dependent on availability of computing resources. But you do not require such large-scale resources always. And you can always do simplified problems, which are important and interesting, also on smaller scale computers. Say, for example, 2D simulations, where you have some symmetry in your system, you can perform 2D simulations, etc. Different, depending on the problem, your needs of the computing resources are determined. So, as I said, we require basically a good infrastructure of large-scale high-performance computing facilities. There's one in IUCAA. Unfortunately, we cannot show you that because you cannot physically come here. But hopefully, if you come here someday, we can give you a tour of that. Also, what becomes more important is as you run large-scale simulations, you also generate a lot of data. And then you have to analyze this data. And even for analyzing data, you also need large-scale supercomputers sometimes, clusters. And then you have to visualize the data. So a person working on simulations have to be good in all of these, both writing codes, understanding the physics, and visualizing the data quickly to make sense of the physics of what is happening. And a typical thing that you'll often hear when you hear about large-scale computing facilities is scaling. So if you take a problem and distribute it into several different processors, how efficient is it? Is your coding such that if you keep on increasing the number of processors, you keep gaining speed? For example, if you just look at the right-hand side plot, this is a plot that I've taken from the Pluto manual. So the y-axis gives you the time required. Let us look at the left-hand side plot. This is a speed-up plot, and this is the time to solution. So the y-axis tells you the time required, and the x-axis is the number of processors. So you can see this is almost a power law scaling, and this is very close to the ideal scale. So as you increase the number of processors, your time to solution keeps on decreasing. And while writing a code that is efficient, we have to keep in mind that such kind of scaling properties are demonstrated. Otherwise, you will not be allowed to run your code on large-scale computing facilities. For example, it also depends on the kind of problem that you're trying to solve. So, for example, sometimes it happens that your code performs well for the first 1,000 processors or so, but then it has a bottleneck. because you have a lot of message passing and interactions between different processes. And if you have too much intercommunication between processes at a given time step, that creates a bottleneck. And even if you put in a lot more resources, that just simply crunches the solution and stops you from proceeding further, getting any further speed up. So just increasing the number of processors does not always mean that you are running things faster. You have to ensure that your basic algorithm of the code that you're developing is also efficient to show such scaling properties. Now, I will talk about a special class of simulations called which is called the Godunov, based on the Godunov scheme. So I'll discuss that. So for going on to that, I just wanted to flash this set of equations which you must have learned now from your fluid dynamics course. So this is the basic equations that describe the evolution of fluids. This is the mass conservation equation or the continuity equation. This is the momentum equation. This is the pressure equation or the energy equation, as somebody must have taught. And this is the induction equation that comes from the Maxwell's equation for the del B del T term. So the equations written in this form are called the primitive equations, where you express the evolution of quantities such as the density, the velocity, pressure, and the magnetic field. But we can recast the equation in a much more easier to implement form, a form that is easier to implement numerically, and that is called the conservative form. So then we do a transformation of the variables from the density, velocity, pressure to density, momentum, and energy. And this is how it looks. So this is just a way of transforming the previous equations in this way. So this is again the same mass conservation equation, but you're just taking the divergence outside, and you have a divergence of a flux. Similarly, this is the same, the momentum equation, but now, the force equation, but now we are evaluating the time evolution of the momentum, rho times velocity. And then if you do that, then you'll find that the other terms can again be represented as a divergence of some quantity here. And so on and so forth. The Xi is energy, and the magnetic field also can be written in this way. So all of this equation, as you can see, has a very standard form, which is a rate of change of time of some quantity plus a divergence of some flux f or some vector which we call a flux equals 0. Or maybe there can be source terms here, but we have 0 source terms for this initial stage of the equations. And this is called a conservative form of the equation. Why is this conservative? Because what it shows is the rate of change of some quantity inside a volume is directly related to the flux of that quantity. So this can easily be transformed using the Gauss's theorem to fluxes of these quantities over a surface. So if you have 0 flux over a surface, so you just perform a surface integral using the Gauss's theorem, then the quantity inside will not change. And this follows from the basic principles of the divergence of the divergence B equals 0 and other concepts you've learned in your electrodynamics. So that is why this is called the conservative form of the equation, and this form of the equation is very easy to implement in numerics. And all of these equations are closed by an equation of state, for an ideal equation of ideal gas with a constant specific heat of CV, CV that is constant, gives you rho epsilon equals to P by gamma minus 1. So this is called the caloric equation of state for constant specific heats. And some of these quantities inside the fluxes are actually tensors, as you can see. So I've just given in the notes here what this term actually means. So if you break up this term, it's much easier to understand if you work with the indices for one of the axes. You'll find that you can break up these terms, and this will become divergence of rho v, and in this way. And you put them back in the previous equation, you will get back the previous form. So it's an interesting exercise for if anyone's interested to derive the conservative form of equations from the primitive form of equations. Okay, so we have now two different ways of writing the equations. And depending on how you write the equations, you can also develop two different schemes. For example, if you work with the primitive form of the equations, you can directly discretize your spatial coordinate into individual elements and use the standard discretization rules that you all must have learned in your lectures in numerics in your courses. For example, this is the centered spatial derivative, second order accurate, forward derivative in space, etc., etc. And there are some cores which actually discretize the space and write the fluid equations in terms of finite differences. For example, the pencil code, which is accurate up to sixth order because of the properties, because you can easily implement finite difference schemes. The problem with this scheme is if you have some discontinuity, then as you can understand, the derivatives blow up. So this kind of a discretized for finite difference-based scheme is very good for systems where there are no shocks. For continuous, well-behaved fluid properties, you can very accurately evaluate all fluid quantities. But if you have shocks and discontinuities or sharp changes in your system, where the gradients start blowing up, then you are in trouble. But the conservative form of the equation has an advantage. So in the conservative frame of the equation, what we actually derive, so this is the finite difference scheme where you have defined a grid like this. So the grid points are, say, at each of these vertical bars. And your quantity there in the finite difference schemes are defined at the center. In the volume average schemes, here again, all the quantities are defined in the center. But this center quantity is not exactly at the center, but this is a volume average quantity over this entire volume defined by these two vertical bars. So now you again discretize the space in certain finite elements, but your fluid properties are assumed to be volume averages within the system. And since now you're writing the equations in a form that is given in a conservative form, as you can see, you do not need to evaluate any of the divergences, any of the derivatives. So if you write the equation in this form, del u del t plus divergence of this, all you need to do is then integrate this over the surface. The divergence goes away because of the Gauss's theorem. And all you need to do is evaluate the fluxes at the surfaces. So your scheme becomes an integral scheme compared to a differential scheme. So even if you have discontinuities between two cells, for example, here, if you have sharp changes between two cells, since you are performing a surface integral of the fluxes here, all you need to do is evaluate the fluxes using a surface integral at this point, and then you can solve the equations without resorting to the finite differences. This will become a bit more clear in the next few slides. So this is the advantage of the finite volume scheme. So the earlier was a finite difference scheme, and this one is called the finite volume scheme. So this is widely used. The only drawback of the finite volume schemes is the current implementation of finite volume methods in the numerical literature is only up to second order accuracy. There are schemes for higher order accuracy, but they're difficult to implement and parallelize. So the majority of the finite volume schemes that we have are only up to second order accurate, which is fine depending on the kind of physical system you want to study. So just to give you a basic introduction of how we solve the finite volume integrals here and what is involved here. As I said, this is a conservation relation in 1D. So this is, say, the evolution of one of the conservation relations, be it density or the momentum or the energy, etc. All can be written in this form, but in one dimension. So it can be written as del u del t plus del f del x equals 0, which is the derivative of the flux. Now this flux here, now we are dividing this. So this is the evolution in time, and these are the discretized coordinates which gives you the fluxes at each of these elements. So now we can approximate this derivative term as an integral over the fluxes over here. Okay. So that is why we are integrating over the fluxes and then replacing it, the dx by delta x, which is the separation. And then we are performing this time integral between the current step, which is Tn, to the next time step, Tn n plus 1. And we can get the time evolution of this quantity in this way. So all we need to do, so this is first order in time. We can also implement higher order temporal schemes, for example, the Runge-Kutta schemes, etc. But what you need to understand is the main crucial point of this is the fact that all we need to do is evaluate the fluxes here. So once we get the fluxes of these quantities, and what are the fluxes? The flux for the mass equation is rho times velocity. Flux for the momentum equation looks something like this. This is given in the form of a tensor. So all we need to do is evaluate the fluxes at the cell edges or at the interfaces of the cells at an intermediate time step, and we can solve the time evolution of the equation. So the main steps involved are the fluxes have to be evaluated at the interfaces, which is something called the reconstruction. And this fluxes, so at a given time n, we can always find the fluxes at any point by interpolating the solution. But what we need to find, as you can see, this is n plus half, so fluxes at the intermediate step. And for that, we have to solve something called the Riemann problem, where, let me go to the Riemann, let me go to the Riemann problem first. The Riemann problem states that if you have an interface where you have a left state of a quantity and the right state of a quantity at a given time t, at a later time, you can find the solution by solving the Riemann problem using the method of characteristics. So if t equals 0, if you have a left state and a right state, which if you remember from the discretized system, these would be the quantities at one of the cells, and this would be the value of the quantity at the other cell. So this is the interface between these two cells, and if you have differences between these quantities, you can solve this Riemann problem. And there are well-defined schemes to find out the evolution of this quantity described by this problem. So, yeah, I think I have already mentioned these things here. Okay. So, essentially the main problem of fluid simulations boils down to solving the Riemann problem at the interfaces of different fluid cells. Okay, so solving the full Riemann problem is cumbersome. I have not included any slides on that here. What it requires is solving the full fluid equations in a matrix formalism using the method of characteristics, find out the eigenvalues and the eigenvectors. That gives you the time, and that can give you the time evolution. But then we can approximate this step by assuming certain assumptions, and then we can develop certain approximate Riemann solver schemes. I have listed a few here called HLL, HLLC, rho, etc. And we use one of these approximate Riemann solvers to find the evolution of the fluid quantity at the cell interfaces. And then, as I said, when you solve the Riemann problem, you get quantities at the interfaces. But to get the quantities on the interfaces, you also have, so your basic definition of the fluid properties are always cell-centered. So this is a volume average of the quantity performed over the entire range of a cell and represented at the center. Now, you can always assume that your density, for example, let's say, is piecewise constant. So between each of these cells, the density is flat. So this is called a piecewise constant representation of the quantity. But it can be that the density distribution has an inherent distribution in between the cell itself. So the fact that we are assuming a piecewise constant is because all we know is the volume average state of the quantity, but it can vary inside each cell as well. So this is a further refinement that we often perform. And this is a linear, yes, there's a question. I'll just come to your, keep writing in the chat. I will come to your questions in 5 minutes or so, and then go to the next phase of the lecture. So what we often do is we assume that the fluid is not just constant, the density is not constant between these two interfaces, but has some profile. We approximate that either by a linear profile, which can look like this. So this is called the linear reconstruction. Or we have a second order profile, which is a parabolic term, and just add an x squared term, let's say. And so what essentially we do is we assume that the quantities inside are not just represented by the simple volumetric average quantities here, but they have a profile. And this adds to the accuracy of the solutions that we finally obtain from the Riemann problem. So this is something called the reconstruction step. Okay, so the reason why I highlighted these steps are when you actually try to run Pluto, you will have to choose several numerical schemes for each of these steps, and having a brief understanding of these steps will help you to sort of connect to what you're actually doing. So this is the standard flowchart for carrying out the simulation. So at t equals 0, you initialize the data at the centers of each cells. And at the next step, then you perform the reconstruction of the fluxes at the cell edges. So what you define is some quantity at the center of the cell, let's say. So you have discretized your space, and you assume that you're at each point in the discretized coordinates, each center point has some value which you have defined at t equals 0, which is the initialization step. Now, as I told you, the Riemann problem requires you to evaluate the quantity, evaluate the fluxes at the cell interfaces. So if you have a density value here and a density value here, you can always interpolate the density from here to here, and similarly from here to here, right? So this is what you're doing. So we reconstruct the density, assuming some reconstruction polynomial given by here, to the cell interfaces. Now, once we have the value left and right of a given cell, we can then perform the Riemann solver. We can then solve the Riemann problem and get the solution of the Riemann solver. So the Riemann solver gives you the final solution at the fluxes, and then you integrate in time. So Riemann solver gives you this, the values of these fluxes. Okay. Now, with the values of these fluxes, then you perform the time integrals. This is a first order integration in time. You can also perform second order, fourth order integration using various numerical schemes for time evolution. So then you evolve in time schemes for time evolution. So then you evolve in time. You check if your code is due for an output, then you write out the data, and then you keep on doing in this loop till you reach a criteria that you want to finish. So this is an example of a fluid simulations that I have, for example, performed in the paper in 2018, where you're seeing where I've been trying to simulate jets from relativistic, from a supermassive black hole. These are relativistic jets. I'm sure Professor Saikia has taught you now about what are jets from supermassive black holes, and you've heard about AGNs and AGN feedback, etc. So this is one such simulation where you have say this is a volume 3D volumetric image of the same thing, and this is a slice of the 3D volume, and this is a dense distribution of gas. The scales are in kiloparsecs, so the radius of this gas disk is 2 kiloparsec. We have a jet that is coming out from the center. It is interacting with the gas here and then coming out. And this is an actual picture of Centaurus A with a dust lane here. So what we are simulating to give you the reference of the scales is something that is very small. So this entire region is 60 kiloparsec for Cen A. And what we have done in our simulations is just a central region here. And I'll just let you see the movie. It looks quite good. So this is a big bubble that the jet blows up. And what you're seeing is density, log of the density. So, and the contours represent the beta equals to 0.6 C. So this represents the relativistic part of the jet. So what we really try to understand is how this jet is interacting with this dense gas. It is launching these outflows. You can see this comet-like structures that is lifting upwards from the disk. So it lifts a lot of this gas and creates outflows, and we can detect this outflows through observations. So from the simulations, what we're trying to understand is for different properties of the jet, what is the predicted property that we can observe? And in this way, we can connect observations and simulations and drive the science in the field. So I will introduce this code called Pluto now. And before I do that, I'll take a few questions if there are any. I see that there is one on chat. If any other participants have any questions, please raise your hand. So Pralay is asking, is it possible to write primitive equations even for a non-ideal MHD fluid? Yes, Pralay, it is certainly possible. And if you want to write them, the non-ideal equations in a conservative framework, it ends up with added source terms on the right-hand side. So if I go back to my equation slide, sorry. Just move the chat boxes. So you see on the right hand side, it's all 0. So Pralay, let me unmute you. So on the right hand side right now, everything is 0. If you have non-ideal terms and you write them in the conservative framework, you'll have extra added source terms here, which you have to account for. Does it answer your question, Pralay?
Yeah, right.
Thank you. Yeah. So next is Vaibhav. Let me unmute you first and then read out the question. Vaibhav asks, sir, how do you choose which order of polynomials would be best for reconstruction? Is it just trial and error? Vaibhav, this is a fantastic question. We do not know. And it is often trial and error. The thing is, if you increase the order of polynomial, you get better accuracy. That is invariably true. But increasing the order of polynomial also increases the compute time. So sometimes the error budget of the entire computation is dominated by some other term, and increasing the order of the polynomial does not really help you at all. Sometimes it does. So it is both. It is both trial and error and also a judicious choice of what is required for the particular problem. So often what we do is we start off with a basic linear reconstruction, let's say. The flat reconstruction is not very helpful. The linear reconstruction is good up to first order. Good up to second order accuracy. So that we start off with the linear reconstruction, and we start off with the most basic schemes that we have and see whether our initial setup is running properly. After that, we gradually increase the accuracy levels of the different other schemes. And if we do not find significant changes, we just go back to the previous scheme, because now it is less. It is although less accurate, but gives gaining time. Okay, Vaibhav?
Yes, sir. Thank you, sir.
Right. Abhay, for this movie on slide 16, how many CPUs you require and how much simulation time? Okay, so for the entire simulation, I think this required about 1 million CPU hours. And for each of these, I used to run them on, say, 2000 code. I ran them on a supercomputer in Australia. And for each of the simulations, I had used 3,000 cores. And I used to run them on 24-hour batches. So you multiply 3,000 with 24, divide 1 million by that number, you'll find the number of days I have run this simulation. So Shirajit, next, is the simulation capable of generating onset of turbulence? Yes, certainly we do simulate turbulence in this. The kind of simulations I have done, they are not really suited for studies of turbulence, because we have not resolved the internal structures to understand the evolution of turbulence. But of course, there's a wide variety of simulations that do turbulence using the finite volume methods. So turbulence, so I must give a caveat here. So both the finite volume method and the finite difference methods are very good for understanding turbulence. However, for certain cases, finite difference is better because it is accurate. It is more accurate. For example, if in order to study MHD turbulence and something, for example, called the MHD dynamo, due to the turbulent action of the flow of the field, the magnetic field, the mean magnetic field increases in magnitude. There, it starts off from a very small quantity, say nanogauss, and then increases exponentially by several orders of magnitude. And since the rise in the magnetic field or the mean magnetic field is very high, you need good accuracy to sample that rise. So for those kind of studies is usually the pencil code that is widely used and the standard mechanism toolkit that is used, let's say. However, for those simulations, if you have supersonic turbulence meaning that you drive systems, you drive motions in your fluid that are higher than the speed of sound. And if something becomes higher than the speed of sound, then that perturbation will travel faster than the speed of sound and create shocks. So for supersonic turbulence, that becomes a challenge because you are starting to create shocks now. For those cases, then the finite volume method becomes better, and just for the stability of the numerical schemes. Anushka, can you please elaborate? Anushka, you have 2 questions, so I'll just unmute you. Anushka Tilekar.
Yes, hello, sir. Actually, I wanted to ask you, can you please elaborate a little bit on the significance of the particle mean free path length in the fluid simulations? And second thing is, we discussed two mainly types of the simulations, that is particle simulation and the fluid simulation. But can the particle simulation can be considered as a subdomain of the fluid simulation itself, because we are considering individual fragments of in the fluid simulation.
Right, Anushka, this is an excellent question. So going back to the first part, let me go back to that slide.
Yeah.
It was here, right? Yeah. So what I meant here was, if you have, say, suppose you are trying to understand the motion of ions moving along a magnetic field. Okay. Now that mean free path, or the typical length scale of the part, will be the gyro radius of the particle. However, if the gyro radius of the particle is of the ion is extremely small compared to, say, you are trying to study the flow of something moving through say, winds from a star, for example, let's say. So the wind from the star has magnetic field. So we have ions moving along the magnetic fields, they're gyrating along the magnetic fields, and also they may be colliding with other ions along its path. So there are two relevant length scales here. But if, for example, you want to study something that is happening over the scale of, say, the solar system, okay? So then the collisions between different particles are happening at much smaller scale compared to the scales that you can resolve with your computational resources that you have. For example, if you have a scale of 1 AU, you want to study the evolution of some accretion disk that is forming the planets. This is a typical system that actually happens in planet formation simulations. Then you can, say, at most resolve up to 1,000th of that scale, because maybe you can have a simulation box that is 1,000 cube in number of points. Then you can certainly cannot resolve the individual particle motions, and so you're in the smallest resolution is still much larger than the particle mean free path. So what happens now is, within your resolution box, the particles are colliding and coming in thermal equilibrium with something. So then in that domain, you have a lot of different particles. So volume average quantities from a thermodynamic point of view are valid. So you now have a well-defined temperature that you can define. You have a well-defined pressure and a density. So that is why your description of a fluid of property of the particle becomes valid, where things are evolving continuously and there are well-defined definitions of the volume average quantities. Okay. Your second question was, I'm sorry, lost your second question. Where is the chat box? Right. So can the particle simulations be called a subdomain of the fluid simulation? Absolutely true. Because sometimes there are certain phenomena that are best modeled by particles, and they are driven by things happening at the particle scale. For example, several plasma instabilities that we study, they happen on scales of the individual particle motion. For example, example that I gave was a gyro radius of the particles. So before a particle makes a full rotation around the magnetic field, certain things can happen. So if you want to model the evolution of particles at that scale, then you have those phenomena have to be done with the particle simulation. Of course, those particles are part of a larger fluid. But for the larger fluid simulations, you cannot really resolve this individual particle motions. So the particle simulations is, of course, the best way to describe things, because they are well-defined equations that you can follow. But it is not always possible. So sometimes what we do is we do resolved small-scale simulation. One particular example is when you have, for example, two magnetic fields that are coming close together. Now, if the magnetic fields are oppositely directed, they will reconnect, and then due to the reconnection, they can lose energy. And particles or individual ions or electrons that are crossing such a reconnection site can get accelerated due to this magnetic field. Now, from the point of view of the broad, large-scale motion of the fluid, you cannot really resolve such reconnecting layers, because it's very small and thin compared to large-scale structures. There, what we do is we model this reconnection layers separately in a particle-based simulation or a PIC simulation. and then use those results in the large-scale simulations if we require it. So, of course, the particle simulations are form a subdomain of the large-scale simulation, and it depends on the problem that you have. So, I will stop the Q&A here and go to the next phase, which I wanted to show. I wanted to briefly give you an overview of this code called Pluto in the remaining 10 to 15 minutes that I have, and take further questions. So I am giving you the overview of this code Pluto because Pluto is very easy to use, and if you have studied fluids and fluid dynamics in your courses, and if you're interested to follow up on your own, you can use this code without any supervision. It's quite easy to use as long as you know your fluid dynamics or the theory of the fluids. So let's get on to it. So Pluto is a versatile magneto-hydrodynamic code with lots of different modules that it can be used for. Other codes like this are Enzo, Ramses, Flash, etc. I've just given a few lists here, which are used for all of these codes have certain speciality in them, which is good about them to be applied to a particular kind of problem. Although all of these codes can address any given physical problem, provided it has the capabilities to handle that. For example, for Pluto, it is a very well-defined Riemann solver for handling relativistic flows. So this is not GRMHD. So no variation of space-time, but bulk flows that are relativistic. There you have to solve the relativistic equations of motion in a Minkowski metric, and Pluto is very well set for handling this. So, for example, relativistic jets from supermassive black holes, relativistic blast waves, shock waves from gamma ray bursts, as you have learned from Shabnam's lecture. All of these are modeled using Pluto, and it's freely available from here. So when you open Pluto, what you have to do, so this is just giving an overview of the setup. I will not go into the details of this. But when you go to the source directory of Pluto, you will find that there are these following directories. What will be really relevant for interested person is this directory called SRC, because SRC has all the individual routines for the different functions of Pluto, and Pluto is written in C. Inside tools, there are helper routines for visualization using Python or IDL or even GNUplot, and then there are some test problems. So if you're a new user and if you're really keen on understanding or running things on your own to give a hands-on experience, you should download Pluto and go to this directory of test problems and pick up any of the standard test problems and run them. Then go to the tools section, use your preferred choice of visualization, either Python or IDL or GNUplot, and then look at the data, load the fluid variables, the density, pressure, etc., and visualize them using the tools given here. It's very simple and straightforward. Just look at the examples given in these directories, and you will be able to do it without any supervision. And you can perform simple experiments like the Kelvin-Helmholtz instabilities, Rayleigh-Taylor instabilities, flows between different directions, etc., and learn how fluids behave. And most interesting things about fluid is fluid equations are nonlinear because of this v dot del v term in the momentum equation that couples modes from different wave vector space into each other, and that makes things nonlinear. So this nonlinearity in the fluids makes it very interesting, and it becomes a necessity to compute them using numerics rather than analytical solutions. So this is what you get when you do the problem setup. I will skip this slide, but the first thing that you have is something called a definitions.h file, which you have to run a Python script in Pluto to get this. I will maybe okay. I'll show you this step right now live. So I'm just skipping that. So then you have to choose the various physics modules. For example, you have to choose between hydrodynamics, MHD, relativistic hydro, relativistic magnetohydro, etc. You have to choose a time stepping scheme. For example, the one I showed you was first order in time, the one for the Gordonov scheme, but you can have higher order schemes. For example, the RCAA2 with the 2, the PPM scheme, which is the third order scheme, etc. You have to choose your geometry, whether it's a Cartesian system, cylindrical, spherical, and other choices. And then you have this config directory. So if I go back, this is the config directory. there it has some predefined templates of choices of compilers. I'll show you that, and you have to choose one of them to run the code. And then you have this pluto.ini. For example, this is in the ini file, we initialize certain settings. For example, this is how we define the grid. This is the x1, x2, x3. And the first column gives you the number of grids. So if it's just a uniform Cartesian grid, you just have one here. We sometimes tend to have 2 or 3 grids. So the first region is defined by uniform grid, but the second region is defined by some other grid, for example, a stretched grid where the cells are increasing in size because we do not need so much of resolution. So here then it would be 2. And those examples are given in the user manual. This gives you the starting point of the grid. This is the ending point of the grid. How many cells you can give between these 2 start and end points. And the U denotes the nature of the grid, which U means uniform. And this is the schematic of a grid of the Pluto. So the grid starts from the actual computational grid over which your computation will be performed is given by the solid grid here, with the beginning coordinate ibeg and jbeg and in and jn. But this dashed line is an extra padding of cells that we add because sometimes, for example, we need to perform some derivatives. And to perform the derivatives, for example, let's say we want to do the second order accurate schemes. For second order accurate schemes to be performed here, we need information at the boundary, inside the boundary. So these are the boundary cells, and how many paddings you need depends on the type of the scheme. So the accuracy of the scheme, if you have a third order accurate schemes, you might sometimes need 2 other cells here because you need, for the end point here, you need 2 cells over here. So when you actually initialize Pluto, you have to initialize both the boundary as well as the internal domain. But the major computation will be performed at the internal domain, and you have to also provide a boundary condition, as you'd all know from your solutions of differential equations. Then the next important part that you have to take care of is this thing called the CFL. So CFL is this value here, and what it does is it determines the time step, the maximum time step that your code can take. And this is determined by the grid or the width of resolution element divided by the fastest wave speed that is there in your domain. For example, in a typical system for a non-magnetic system, the fastest speed could be the sound speed or the bulk velocity. So V fast could be the fastest of either the sound speed or the bulk velocity. If you have now magnetic fields, you have other waves that also contribute to this solution. You can have the V fast could be either the alpha speed, the magnetosonic fast and slow speed, the fast speed, the slow speed is also, of course, slower, or the actual bulk speed of the motion. And your time step should be smaller than this. Otherwise, you end up with numerical instabilities. So this is called the CFL criteria, or the Courant-Friedrich-Lewy condition. I don't have time to explain what is the importance of this, but people who are interested, I'll always refer to the book called Numerical Recipes in C, and look at the chapter on partial differential equations, and there look at the discussion on the CFL criteria to understand the physical intuition of what CFL actually represents. Now then it's a boundary condition, as I told. For example, if this is the compute domain and this is the boundary, there are different forms of boundary condition. One is called the outflow boundary condition, which in the technical mathematical terms would be the Dirichlet boundary condition. Which is a zero gradient, this is still a Neumann condition, by the way. Sorry, this is a Neumann condition, but with a zero gradient condition. And why is zero gradient an outflow? Zero gradient means we just copy the value of this cell into the boundary. So if you copy this here, the gradient between this is 0. But essentially what you're doing is you're letting this element come that is reaching the end to just pass out of the boundary. And that is why it is notionally called outflow, but mathematically it is a zero gradient boundary condition. But then you can also have a reflective boundary condition. For example, you want to reflect the velocities. If a hard mirror, things go in and then get reflected back. There, what we define is something called the antisymmetric boundary condition, where you take this quantity here, and then at this immediate cell next to the boundary, you give a negative of that quantity over here. Similarly, for this cell, you give a negative of the quantity over here. You see? So this is an anti-symmetric boundary condition. What this ensures is if you have a positive velocity here, the velocity goes through 0 here. And then the boundary conditions is such that the continuity of the velocity component is maintained, but it is 0 here. So that is why it becomes reflective. So at the point of impact at the boundary, the velocity is 0, and this negative velocity will then create this wave to just get pushed back in the other direction. And then you have various output criteria. And so the main function files you have to edit is the init.c. I'll quickly see if I can show you the actual live demonstration. So I'll give this PDF on the course website. So I had set up a simple problem called the Kelvin-Helmholtz problem. So as you can see now, I hope you can see my screen. Let me increase the font size, yes. Yes. So initially, when you start off, you would have this something called the init.c, which gives you where you have to give the initialization of the input variables. The init.c looks like this, where you have a function called init, and inside the init function, you have to give the variations of the various fluid quantities. For example, the density rho, the velocities vx1, vx2, vx3, the magnetic fields, etc. Then the next important part is the pluto.ini. This I already have given you an overview, but this is how the actual file looks like. You have a grid section where you define the number of grid points and the beginning and the end points of the grid. Here is a CFL block where you give the CFL criteria. Here is how you define your boundary conditions. For example, for this one, I have periodic boundary conditions in the left and right. And this is how you define what is the frequency at which the code will output my files, and the nature of the output. For example, it will output all the fluid variables, density, velocity, etc. And these are other parameters which are not really relevant. So the way to run the code is so you call this setup.py script, and it opens this nice GUI. You go to setup problem, you can see that there are several different options. You can cycle them using your arrow keys. For this problem, I have MHD. I have the two-dimensional problem using a Cartesian grid. There are no external body forces. For example, gravity, there are no gravity. No cooling as well. We have a linear reconstruction, as somebody was asking, what is the nature of the reconstruction? We have other schemes, Limo 3, parabolic, MP5, etc., flat, but we use linear. Time stepping, this is the second order Ruger-Kutta, third order Hancock, etc., etc. We'll use second order. And in this way, you can just, in a simple way, choose different schemes. You have to choose your equation of state, which for this case, I have assumed an ideal gas. And this is something that I have not described, is there are certain schemes used to control the fact that the divergence B equals 0 is maintained. And I have used something called the constraint transport. These are all well described in the manual. And you are done. Then is a change makefile. So this lets you choose one of these options. So Darwin are list of compiler options useful for a MacBook. Linux GCC is one that I use for a simple demonstration like this. And this is for a GCC compiler in a single core processor. And Linux MPICC is compiler flags optimized for a large-scale MPI-based run. And I am done. Then I make. The J2 is a parallel make, which is just a trick to make the make scheme faster. Okay, then I run Pluto. For a single processor scheme, the output is given on the terminal. You can see it is running. So I'll just give you a brief description of what these numbers mean. The first is the step number. This is the time. This is the DT at that particular step. This gives you the percentage completion. And this is the Mach number. So the Mach number gives you the highest Mach speed in the entire domains. And Mach number is the the velocity of the local velocity divided by the local sound speed. So the thing is, if you have a strong Mach number value here, which usually means that you have encountered a shock, you can see that till the end of my simulation, I'm still subsonic, which means everything was fine. So now that I have run, you'll see that I have created this .dbl files, and these are the Pluto data files. So each of these data.dbl have all the fluid variables encoded in them. Density, pressure, velocity, and magnetic field. Now, these are binary data files, and there are helper routines in the Pluto distribution to help you read them, or you're welcome to write your own routines. It's very simple. And I have already prepared a Jupyter notebook for this. For example, I have, okay, let me. Okay, so I had already run two different setups. So this is the Kelvin-Helmholtz instability that I have run. And I've run them for two different magnetic fields. And I've already loaded the results because of lack of time. So this is how it looks. Okay. So what I've done was, so this is the simulation that I ran in front of you right now, and for two different magnetic fields. So what I have was, there are two different fluid flows. So the top is moving towards the left, and the bottom is moving towards the right. So there's an interface, and at the interface, I have slightly perturbed it by a sinusoidal function. And what I'm plotting here is a fluid tracer. I have colored the fluid on top with yellow and the bottom with another number, which I'm representing here. And this is an ideal setup for something called a Kelvin-Helmholtz instability, where you have two layers of fluid flowing opposite each other. And if there's small perturbations, you have these two different fluids with two different velocities start to interact with one another, and so you'll see what happens. And I've also, as you will notice, I've introduced a magnetic field. The magnetic field is along the x-axis, but for this first run, the magnetic field was very low. So as you can see, the magnetic field quantity is 0.1 in some normalized units for this case. And the next case, the magnetic field quantity would be 1, which is 10 times stronger. And you'll see the difference, what happens. So as the simulation evolves, I hope you can see it. You can see that small scale wiggles start forming. And this is a direct demonstration of something called the Kelvin-Helmholtz instabilities. And if you do the linear stability analysis of Kelvin-Helmholtz from theoretical point of view, you'll find that the fastest growing modes are the smallest modes. So the smallest modes here would be given by the resolution elements of the simulation. So that is why the first eddies form are closest to are of the size of a few resolution elements of the simulation. So you can see the large scale structure still remains a broad sinusoid, but you start developing the small scale eddies, and the small scale eddies start growing. You can see they are growing now. And each of these small scale eddies are merging to become larger scale eddies, and then they're overtaking the entire box. And by the end of the simulation, you have this nice vertical structures. And this was done with very poor resolution. Otherwise, you can nicely resolve these structures here. Sorry, this was another case. So this is a typical vertical structure you find in nonlinear development of the Kelvin-Helmholtz instabilities. You'll see that when you have two streams of motion, for example, clouds, fast-moving clouds moving past one layer of the atmosphere, you have this Kelvin-Helmholtz vortices that come up. This is a very nice example of this. Now, what happens when we increase the magnetic field? So, for example, this simulation had a magnetic field value of 0.1. Now, when I have increased it by 10 times, let's see what happens. Okay, let me load all of the data points here. All of them are not loaded here. Oops. Okay. So forget the first one. So this is the start point of the simulation. Oh, sorry, I forgot to change the directory. So this was still 1 point. Okay, so this is the start point of the simulation. You can see that some instabilities were indeed picked up, but they completely diffused out and died. And by the end of the simulation, these are actually numerical artifacts. This flattening are numerical artifacts. So the Kelvin-Helmholtz vortices we saw in the last case are not there. And this is because of the effect of the magnetic field. The magnetic field, as you remember, is along the x-axis. And what it does is, as the Kelvin-Helmholtz vortices are trying to grow, they have to bend the magnetic field. And the magnetic field has a restorative force that prevents the formation of vortices. And it has a negative impact on the growth rate. So magnetic fields can suppress Kelvin-Helmholtz vortices, but that strongly depends on the direction of the magnetic field. If the magnetic field are along the direction of motion of these two layers, then it will suppress. If the magnetic field is perpendicular, then it will have no effect and the vortices will develop as if there is no magnetic fields. Okay, so this was a nice little demonstration that I wanted to share, and I'll stop the lecture here. I'll wait for any questions if people have. And so you can raise your hand or you can also write in the chat box. So I can see, Vaibhav, you again have a question. So let me, while others are raising their hand, I'll unmute Vaibhav and also read out the question. So what do you mean we have a borderline condition? For example, protoplanetary initially can well be approximated fluid. As it evolves, metastatic and dense, new planetesimals forms majorly follow particle formulation. Okay, so I think, Vaibhav, this was a bit misunderstanding. So I'm not saying that inside the protoplanetary system, as new planetesimals are forming, we have to go to a particle-based formulation. You can still denote those planetesimals as being embedded in a fluid and describe them as a fluid property. But what I meant was there are certain properties which are best described by a particle nature. For example, there's winds, the solar winds, for example, moving out and interacting with these planetesimals. They can have separate phenomena that are affecting things on the gyro scale of the particles. So those kind of phenomena cannot be caught in a fluid simulation. And for that, we need to go to the particle-based simulations. So the fact that the planetesimals are forming and they almost behave like individual particles, and that is why we are saying whether they are subdomain, the particle simulations are subdomain of fluid simulation, I think that is not right. Does it answer your question, Vaibhav?
Sir, I had one question. If we encounter a situation where we need to use the particle formulation now, how do we change? Like, do we have a different code for that? And
yeah. So that's a completely different simulation. We cannot do everything at same time step.
Thank you, sir.
Okay. So Shurajit, you have a question? Shurajit, unmute and ask the question.
I have written it in the chat box. I mean, if the fluids have charge, so that the magnetic field has effect on it.
Yes. So these are ionized fluids.
So plasmas. These are
plasma. Yes.
Okay. All right.
Okay. Saurav, I did not understand your question. So, Saurav Upare, can you please unmute and ask the question?
Am I audible?
Yes.
Hello, sir.
Yes.
Sir, I was saying that while we are using a Jupyter notebook, so I'm also using a in Replit. There's a Replit one.
Yeah, you can use whatever is preferred for you. I just gave you an example of what that is easy to understand, but you can feel free to use whatever is best for you.
Okay.
Okay.
Thank you.
Okay. Right. Any other questions right now? Anushka. Yes, and Anushka, you're asking, can you take 1 or 2 sessions on this topic, elaborating on some more detail and examples? Only 1 session is not enough. I completely agree with you, Anushka. This is a very rushed demonstration.
Yes.
You can look at my summer school lectures from last year. You'll have a lot of topics that are repeated. But I gave one more example last year. It was also less rushed. I don't have my website up now, but I will upload a few more details on my website after I finish the summer school, because my website is under construction. I have to edit a few things. There, I can link a few more lectures. I've given a bit more advanced lectures on the numerical schemes that might help you understand a bit better. I'm sorry, but I don't have any other lecture slots left for this. Thank you for your interest.
Oh, okay. Yes. Thank you.
And Avinash, sir, how to test the accuracy of the model in case of numerical? So this, I think, is better discussed because I did. Yes. Avinash Patro, can you please unmute and ask the question?
Yes, sir. Am I audible?
Yes.
Sir, we are simulating the astrophysical models. So how so we have to wait to see the astrophysical event to compare with the simulation, or is there anything else to test?
So your question was, sir, how to test the accuracy of the model? So testing the accuracy of the model has a different answer than what the question you asked right now. What you asked verbally was whether we have to wait for the astrophysical model or astrophysical phenomena, etc. That completely depends on whether you are trying to model an observed phenomena, or you are performing a general simulations and then you are predicting something. And that also happens. For example, even for my simulations, we have predicted several things. And then people have gone and observed them with telescopes and found not exact matches, of course, because you cannot really predict actual scenario. It's very complicated. But there are certain morphological similarities with what we have simulated in our work, which people have then found from actual observations and make some connections to the physics. So it works both ways from a philosophical point of view. But the question in the chat, I think it's also important to address it. So I'll just address this anyway. It's how to test the accuracy of the model. It's a very important question, and this is something that we spend a lot of time thinking about when we are developing a new numerical module. So what we usually do is we try to set up a very simple analytical problem first, which has an analytical solution. And then we compare our numerical results with the analytical results and see how far off we are. Of course, from the numerical schemes, you can understand there are several different approximations at several different steps. So we have to calibrate each of these steps very carefully. So for example, keep all other steps fixed, but vary one of the numerical schemes to see which scheme is giving better or worse results. And in this way, compare with a known solution and see whether the level of accuracy is at 10%, 20%, 1%, etc., etc. That is how we test the accuracy of the models. And as you will see in the Pluto test problems, if you ever work on it, there are some things called the shock test tube problems, or the SOD. So the shock test tube problems are actually solutions or direct Riemann problem solutions where you slightly perturb something and see the evolution of the different waves, whether it's a sound wave or the Alvin wave, etc. And we know the exact analytical solutions of this, of where the wave would be at what point and in time. And then we can compare the numerics with the analytical problem. Thank you, Avinash. Saurya also asked, sir, can we simulate more complex things like black holes? Yes, what should I do? Where to start? These are more philosophical questions, which is not very relevant for this discussion. But of course, as you can understand, astrophysical simulations have become matured a lot to include the effects of various different kinds of physical systems and physical phenomena, and do model extremely complex physical scenarios. Of course, we cannot get everything correct because there are several different things happening in reality, but we certainly can get some bulk volume average quantities correctly. And that is what we then try to constrain through observations. Okay, I don't see any hands up now. And I have addressed all the other questions on chat. If there is no other question, then I'll close this session. Okay, so I don't see any other questions. So thank you all for attending and thank you all for listening. I hope I could have given you some flavor of astrophysical simulations, and wish you luck in case you work on this in future. Thank you. Sagar, you may close the session now. Thanks.
Yes, sir.